Hello. Um, so my great colleagues at Golem asked me to give you a very brief overview of the more technical um, aspects of gWasm and what kind of challenges it's trying to address, especially when it comes to security. So I'm going to keep it brief, and I hope not to bore all of you. So let's get cracking. So first of all, very quickly about me. So who is this guy? So my name is Jacob. I'm an R&D researcher at Golem Factory. I'm one of the authors of gWasm. I'm also a member of WebAssembly community group, and I'm a regular contributor and maintainer of Wasmtime and Wuzzy repos on GitHub. Feel free, if you have any questions, feel free to contact me directly. You've got my Twitter handle, you have my email addresses. You can also find me on GitHub. Pretty much whenever you see Kubkon, that was probably me. Like it's pretty unique, I guess. Right. So Golem. So before we get to gWasm, especially for those of you who haven't really used Golem for that long or that much yet, I'm going to very briefly describe what the problem space is. So Golem is a network. It's meant to be a network of computers. You have two types of people, or two types of users who would actually join Golem network, and those would be requesters on one side and providers on the other. So requesters is everybody who wants anything done on the network. So if you have any sort of computationally intensive task, you'd be a requester, you join the network, you would schedule the task, and then the providers would actually compute that for you in exchange for some tokens. Okay, so you can think of it as so requesters are the demand side of the market, and providers are the supply side of the market. We also have one more set of users. They're a bit well, I wouldn't call them users. So they are developers. So basically, those are the guys who they can be users as well, but those are the guys who write apps with the intention of launching them on Golem. So we have a couple of examples of such apps that you could use in Golem using gWasm. That would be the infamous by now, I guess, gFlight, and there's a couple more as well. Okay, so the important bit is to remember that there are those three parties involved in Golem. So what are the challenges? So from the requester perspective, obviously, I think first and foremost, we'd like correct and verifiable results. So if I launch a task on the network, when I get the result back, I'd really like it to be correct. So there are two ways of addressing this. So bear in mind that Golem is what we call an untrusted environment, right? Because you have no idea where your task is going to go to. So you can't, if the result comes back wrong, well, you can't do anything, to be honest. And besides, how do you even know whether the result is correct? And that's actually a very difficult topic, a difficult problem with no one solution, I guess. So in general, I guess you could think of it in a binary way. So to verify that the result is correct, you would either write your own verification logic. So you send it to the provider, the results come back, and then you apply some kind of a function to it to verify that the results are correct. This works, but there is this massive negative side of it, in the sense that you have to do it. So you're like the domain expert or the developer who supplies the app. You should know how to verify that the results are correct. So that's not ideal. Then the next side of the coin is what we call verification by redundancy, and I'm going to get to that later on. Basically, in verification by redundancy, we are able to actually compare the results of two runs together and say, well, and they should match if somebody was actually truthful. Why? Well, because of determinism. So we are ensuring that everything is deterministic. Okay, right. So those two challenges for the requester. I'm going to get back to verification in a minute, but let's briefly describe the challenges of that the provider is facing. So that's mainly, I'm saying mainly, but there's probably more, but it's sandboxing the execution environment. So basically, if I'm the provider, you send me some stuff, I don't want you to gain access to my computer. Well, that would be a disaster. If you were able to insert some kind of a malware or something, that's it, game over, right? So basically, we really care about sandboxing of this stuff. So in general, you could, I guess, have you could think of two ways of doing this, or actually no, that would be actually one. It's just that like subset. So virtual machines, right? You can actually launch a virtual machine, and basically anything that's happens there. You shouldn't get out. That's why we have chosen Wasm, because Wasm by itself is meant to be run in a sandbox environment, so that's perfect. So actually, believe it or not, but Wasm was designed with this security in mind. Okay, and developers. So from the developer's perspective, obviously we wouldn't want to leak any proprietary algorithms, but that's a topic for an entire different conversation. And we also would like secure and licensed app store. I think with Wasm, we can get there pretty fast. Wasm is gaining popularity. I believe there are even some solutions to that out there already. But since Wasm is very much driven, I guess you could say mainly by Rust, Rust.C, and so basically people like Rust developers and people responsible for Rust, I bet it's going to be close to Cargo when it comes to Wasm packages. So that's going to be really cool. Okay, right. So having all those three challenge spaces in mind, let's talk about gWasm. So what is gWasm? Briefly, so gWasm is like a meta platform. So basically, gWasm allows you to launch any sort of Wasm module on the Golem network. So if you're a developer, you can specify some kind of an app like a gFlight that would allow you to convert text to speech or something like this. We envision that we're going to have some kind of a Wasm app store thing. But anyway, as a requester, you would just automatically pull it, and then you would just run it, and then automatically that would spread over the Golem network. And carrying the benefits I already mentioned. So we have sandboxed execution environment. We have enforced determinism in gWasm. That means you don't have, as a requester and developer, you really don't have to worry about verification, because that's pretty much handled for you, as I will describe it in a minute. And it's cool. It's Wasm. Right. So how does it work currently? So imagine you're a requester, you specify a Wasm task. What happens then? The task is actually split into SAP tasks. Providers are computing the SAP tasks, then you get the chunks back, and in the logic on your side, you pull the results together. If your basically verification passes, if everything is verified that is correct, you just schedule payments. Everything is obviously done automatically for you, and the payments are done in GNT, so that's our token. Okay, so let's go a bit deeper into the provider's perspective, and that will be the sandbox. So how does it work? So basically, currently in gWasm, we rely on Wasm 32 unknown and script and target. Now, there are 3 targets for compilation to WASM. First one is the so-called WASM32 unknown. I'm actually talking about the Rust triples. In different programming languages, you might have different names for the same thing, but basically the first one is called freestanding WASM. So you can compile your code to it, but you will not be able to do any sort of I/O or anything like this because it's basically not hooked up. So you need some kind of a backend to hook up. So one of those backends is Emscripten. Emscripten is how to describe it best? It's like emulation of Linux inside a browser. So Emscripten uses a lot of JavaScript shims to provide you with all of the functionality that you would normally find in your libc on your OS. The cool thing about Emscripten is that it's been designed with portability in mind. So basically, as a C, C++, mainly C or C++ developer, the main goal of Emscripten was to give you, so basically to unburden you from porting your code to WASM. You basically run the Emscripten C compiler, this EMCC, and that's you done. The minus of Emscripten is that we actually get 2 things. One of in addition to the WASM module, we also get the JavaScript glue code. So it can be hefty file. It's gonna have it's gonna be pretty long, a lot of JavaScript shims. And the last target, and I'm gonna briefly touch on that later on towards the end of the presentation, is WASM32 unknown Wuzzy. Well, no, actually, sorry, that was wrong. It used to be called like this. Now it's actually referred to as WASM32 Wuzzy. So Wuzzy was a response of Mozilla initially, I guess, to exactly the problem that we're presenting here. So basically, you want to take Emscripten out of the browser and use it like a typical virtual machine or sandbox. But with Emscripten, as we have here, you have to fight with JavaScript. It's emulating entire Linux, which is not ideal. So if you actually wanted to hook up an actual host file system, it's not that easy. It is doable, but it's not easy. It's kind of messy. It's very easy to do something wrong. So Wuzzy was a response to this in the sense that it's based on a couple of very cool standards projects, I guess. One of them is Cloud Abbey, which features a very restricted set of syscalls on the host. So that basically gives you a much, much narrower surface of attack and surface of actually API that you have to worry about when you're actually talking to the host operating system. And they're pre-open, so basically Wuzzy gives you capabilities. So WASM module is not able to do anything unless Wuzzy module is not able to do anything unless you explicitly give it permissions to. Right. So coming back to our sandbox in Golem that we currently have for gWasm. So that's based on Emscripten. You get basically 2 modules. One is WASM, one is in JavaScript. And then you need both. So basically you package them both together into a Golem task and you send it off to the network. Now on the provider side, he's basically running that in this beautiful box. And that's actually a SpiderMonkey based sandbox, you could say. So basically we embedded SpiderMonkey engine that you find in Firefox to run. So basically to compile and instantiate WASM module and then do the work. Everything is happening in the host memory, as I said. So basically with Emscripten, in our case, we try to avoid hooking up the file system. So basically, well, actually, let me get to this. So, there we go. Right. So on the left, we have the host, and on the right, we have the guest. Now, on the host, we have our actual file system. So this is we're inside a folder called workspace, and we have there the JS module, hello.js, and hello.wasm. We also have, if you notice, 2 folders. One of them is in, one of them is out. Obviously, naming can be different, but in will have the input data for the SAP tasks, or well, for the actual WASM program, and out, this is where we expect for the output to land in after the provider finishes with it. Now, when we send it off to the provider, what happens there is that all of this stuff is actually loaded into provider's memory. It's actually not, so the sandbox does not well, WASM doesn't have any access to the host file system. So from the provider's perspective, you can be sure that you're actually that little bit more secure in the sense that everything is in RAM, so they don't really get any access to the file system. A big negative point about this is that since since everything is in memory, if your WASM program is quite big, it can explode. So that's not ideal. So with that in mind, because everything is in memory, everything is so your WASM module, essentially speaking, is given to access to this virtual root file system. So you can actually do anything, and because it's Emscripten, actually emulates a lot more than you actually need. So basically, you can open in.txt as it is. You can then create out. You can create a directory, and even save a file to it, and everything will work. So basically, when all of this is created in the memory FS, as you can see on the right-hand side, sorry, then this bit, after it's been done, so this is towards the end of the run in the sandbox, is being copied out into the host file system, but only into this one folder called out. This is it. And this is outside of the WASM space, so this is actually done after WASM has been executed. Okay, and then everything is then packaged for you and then sent back to you as the task results that you can then verify. Right. So now, requester's perspective. So this is very interesting. Verification of results. So as I was saying, there are two main ways of approaching this with gWasm, because gWasm was made with this. When people conceived when people conceived WASM, they have actually made sure that non-determinism is kept to the very minimum. So with pure WASM, at the moment at least, the only non-determinism that can appear is in the representation of nonce, so not a number, on the given architecture. But if you're running on the same architecture, so if you have the same program running on two hosts featuring the same CPU, for instance, then that problem disappears. Okay, so not going to go there. Now, WASM being deterministic, or quasi-deterministic, I guess, plus if you can patch up the non-determinism in Emscripten, such as access to random numbers and things like this, basically what you then have is that your WASM programs are deterministic. So that means if you run them on two different providers, you can actually compare the results byte by byte, and if nobody has lied to you, they're going to be exactly the same. Okay, this is a very powerful feature, and this is exactly what we've done, which means that all that's required for you to be sure that you're getting correct results back in Golem in this essentially untrusted environment is that you basically send one task to two providers and then you compare the results. So what I mean by this is that your task is duplicated. It will cost a little bit more, but in the grand scheme of things, this is a good thing, because then you don't have to spend so much time, like your valuable time, on coming up with this verification function, or God forbid, verifying the results by hand. I mean, that's basically impossible. So then you send those two tasks to two different providers. Then they compute that. They give you the results back. If the results do not agree, then you launch the task again. You send it to the third provider, and he's basically like this tiebreaker. So then if any of the two match, then you only pay those two, whereas the third one who's lying, he gets a penalty. Okay, so actually it's pretty cool. It actually works pretty well, and it saves you this hassle with trying to come up with the verification logic by yourself. So now this is very, very exciting. So how can you actually enforce determinism in Emscripten? So the first thing is obviously random numbers. So I actually call it random device emulation. So this is covering anything from access, like on Linux at least, or Mac, access to the raw def random device, or using any of the Emscripten libc calls, such as oh god, I think it's rand from within Wasm. So believe it or not, this one was actually pretty easy. And that's mainly because by default, if you're not running in the browser or node environment, and Emscripten knows this, because certain markers are set, then you'll actually get a panic whenever you want to access randomness. So basically, the way we patched it up was we essentially speaking return every single time you run your Wasm module and you get random values, you get exactly the same repeatable stream of numbers, always. Okay, so that's done. That's easy. A little bit more tricky one was patching up time. So well, it turns out that if you have access to the system time, you're given non-determinism. Why? Well, because if I measure time now and then I measure the time in a couple of seconds, obviously the value is going to be different, and it's almost monotonically increasing, which means you were given a poor, in terms of cryptographic security, stream of different numbers, which basically you could actually implement randomness on top of this. So this is a thing we really had to patch up. So essentially what we did is for any call to system time now or something like this, you will always get the same timestamp 0. So the beginning of so basically the first value of the Unix epoch. So yeah, you can't be too happy. You can never be too happy, I guess. So it turns out that if you do this, you're going to break Emscripten. And how are you going to do this? Well, there is this tiny function called _usleep, which essentially speaking, yes, you guessed it, is for the sleep functionality. So Emscripten, if you call sleep from Wasm, it's going to delegate the function called that JavaScript shim. And if you look closely, this shim, and I guess this is because Wasm is single-threaded, so this shim is actually implemented as a busy loop. So we've got in the while, we have date.now, which is basically give me the time now, and we have minus start. Now if you look up, start was actually also date.now, and it's always 0. So obviously 0 minus 0 is 0, and then whatever you specify as the milliseconds, or actually the microseconds above, even if it's going to be 0, you will always, you'll never be smaller than this. So that means you're going to be spinning indefinitely. And we had a couple of weird bugs because of this. So in the end, we patched it up, doing actual sleep on the running thread. Okay. Right. So in the beginning, I mentioned Wuzzy. So what is Wuzzy? Why Wuzzy? What does it even stand for? So Wuzzy is, it stands for WebAssembly System Interface. I think it's a very elegant name for what it's meant to be doing. It's a standardization effort led by the Bytecode Alliance. Essentially speaking, it's as I mentioned, this is taking Emscripten, or taking the idea of taking Emscripten outside of the browsers, but making it like sound in the sense that it's secure and it's been designed with this in mind, unlike Emscripten. So Wuzzy will require a little bit more effort when it comes to portability, but not that much though. You can still, you know, it's doable. But the best thing is, you do not have to worry about so many syscalls. Like Emscripten tries to emulate entire Linux. There's a lot of syscalls. I think it's close to like 350 or something. I can't remember off the top of my head, but it's a lot. Whereas in Wuzzy, I think you have currently at least a roughly 50 or something like this. The cool thing about Wuzzy, and this is another thing, is that you no longer need the JavaScript shims, because all of this functionality, the implementation of the syscalls, is provided to you by the runtime itself. So runtime in this case could be Wasmtime or Wasmer or Wasm3. And when you compile your Wuzzy module, you basically specify within it that you're going to import certain functionalities from the runtime, such as, I don't know, fd-read, which is used to read from a Wuzzy file descriptor a stream of bytes. And basically, this syscall is provided to you then by your Wuzzy runtime. So yeah, happy days. You don't have to worry about the JavaScript. Again, and additionally, you actually are given access to the host file system, but only as much as you, the user of the runtime, permit. So basically, if I was to give you the Wuzzy module and I wanted to do something shady on your, I don't know, /dev directory, I won't be able to do it unless you specifically say that, hey, this Wuzzy module has got access to /dev. And obviously you wouldn't do that. So you're safe. So it's this concept of capability-based security is pretty powerful, and this is only the beginning. The beginning in the sense that currently Wuzzy is mainly about the file system, but this is changing rapidly. We're actually working on many cool things, such as Wuzzy crypto and whatnot. So everything is evolving. The file system was just the beginning, Okay, so in Wuzzy, the entire model for the sandbox is slightly different, as I was saying. So basically, the first thing that's different is we no longer compile to Emscripten, we actually compile to Wasm32 Wuzzy. We only get one module. Now in the runtime, as I was saying, you're given, we have this concept of capabilities. So in terms of the file system, that would be, for example, access to /dev, which in this case, in this photo, is not allowed, but it will also be access to /workspace, which we want to give it. And for example, I don't know, access to entropy, which would be, hey, give me access to pseudo-random numbers. So basically, so if I give it to you, then you will have access to the syscall that allows you to pull randomness. But for instance, I'm forbidding you from the use of clocks, so you have no notion of time. So it's very much configurable, and it's meant to be secure. So basically, you as the owner of the runtime, you will decide what your Wasm modules can and cannot do, which is perfect for Golem. Right. So I hope that wasn't too boring. Before I finish, I wanted to show you, provide you with a couple of links. Hopefully you're gonna have a look. So this is pretty much, I was gonna say all, but it's probably not all. It's majority of the stuff that we have prepared with gWasm in mind. So the first thing is the gWasm sandbox, and it's on GitHub under Golem Factory /SPWasm. I strongly encourage you to give it a try. If you find bugs, and I hope you will, please submit issues. Oh, bummer. Maybe I'm gonna, ooh, crap. Sorry about that, guys. Maybe I'm gonna move this here. Right. So yeah, please submit issues if you find anything. It's yeah, it will be very helpful to us. Tooling for writing gWasm apps. Well, we were quite busy. You have a couple of things to pick from. You have a high-level gWasm Rust API library, which basically allows you to interface your native Rust app with gWasm. So a good example of this is actually gFlight. So in gFlight, we are compiling in the bytes of the Wasm module in JavaScript, which are responsible for executing the flight engine. So flight engine is actually the text-to-speech engine as Wasm. So you basically, whenever you run gFlight, it automatically packs it up into a Golem task and then sends it off. And then when it comes back, it just pulls it back together and you get the speech file from your text. Important thing to remember is that you need your Golem client running. The next thing is gWasm Runner. So this is a cool app that takes it a little bit further. So I always think of it as on the other side of the spectrum, in the sense that gWasm Runner actually compiles your entire app into Wasm, your Rust app, and then basically allows you to do MapReduce, like to solve MapReduce type of problems on gWasm. And the added bonus is that actually you can use it on Golem, but you can also use it in Golem Unlimited as well. And there is also a C++ equivalent, which is called gWasm Dispatcher CPP. Okay, so for example, as I mentioned, we have gFlight, which is it's actually a full-blown CLI, so you can feel free to experiment with it. Again, if you find any problems, please let us know. We also have Hello gWasm Runner, which is this is a very good entry problem if you want to start using gWasm Runner. And also we've prepared like what I call a curated list of gWasm app examples. So that's Golem Factory /Wasm store. I think we have at least a few, like 10 or something. So have a look, break stuff. It's always cool to break stuff. And I will let us know how it goes, right? As a final note, if you guys have any questions, you can always contact me direct on any of the handles. On Twitter, I'm probably like least likely to reply on Twitter. I don't really use it for direct messaging. But if you ping me an email or you can submit an issue or something on GitHub, I'll be sure to respond to that. Okay? So I hope you enjoyed it. If you have any questions, as I said, feel free to reach out. And I hope to see you guys soon.